Hi, my name is Nikki Sanderson, and I'm excited to share with you about topological data analysis for correlation matrices. So correlation matrices are a particular type of input that is measuring some property of a pair of data points. And unlike distances, this representation of this measurement is going to be high in value when things are similar to each other and low in value when things are dissimilar. So some examples that we have from applications include Pearson correlation, or taking the dot products between certain like feature vectors. And these correlation matrices can also come from more domain-specific similarity measures. Like if we have spike trains between different neurons, we could have a matrix of the spike train similarities where these matrix value entries are higher if the neurons fire similarly and lower values if they're different. And one key thing about these matrices that we're going to be using as input for topological data analyses is that they're symmetric. Now, I want to contrast these correlation matrices with a type of matrix that is often used as an input for topological analysis, which is distance matrices or dissimilarity matrices. And in these matrices, data points that are very similar have low values, and data points that are really different have very high values. So some common examples of this in practice are Euclidean distances, taxicab distances, and again, also more domain-specific distances that might not be a distance or metric, by the axioms of math, but still are measuring the dissimilarity between two different data points. And again, in the context of inputting these distance matrices to TDA algorithms, TDA is an acronym for topological data analysis. The input matrices need to be symmetric. And now that we've talked a bit about the differences between correlation and distance matrices, I want to talk about where TDA stands with regards to these two different types of inputs. So lots of theory has been developed talking about the stability of doing topological analyses on these distance matrices. And also there have been many applications to a diverse set of data out there. And the way that this kind of is applied often is you think about your data as a point cloud where the points are living on some type of shape, some type of manifold. But we don't get to actually see the shape that these points live on. All that we have is this distance matrix between the points. Maybe we were able to get this distance matrix from the space where the points live, or other method. But once we have this distance matrix, what we could do is we could build a sequence of graphs where we add edges between the data points in increasing order of their distances. So data points that are close by get an edge added between them first. So here the nearest 2 points are points 5 and 6. So the edge between 5 and 6 gets added first. The next 2 closest points are points 1 and 2. So we add that edge in the sequence of graphs. And in this way, we add all of the edges and end with a complete graph. Now, what takes us from a graphical analysis of matrices to a topological analysis is that we're going to actually have more information than just the sequence of graphs. We're going to flesh this out by building what's called a simplicial complex or a filtration of simplicial complexes, where at each step, given a graph, if we have any clicks in the graph, we're going to fill it in with a simplex, which is really just a high dimensional triangle. So in this case, we have all the edges between the points 1, 5, and 6. So we're going to fill in that triangle. And as more and more edges are added, we start filling in tetrahedra and higher dimensional simplices. And by the end of the filtration, we have a full click on the entire set of data. So we just have a very high dimensional simplex there. And so what persistent homology, one algorithm in topological data analysis toolbox, does is it computes the number of homology cycles in various homological dimensions as a function of this filtration step. And so what Betty curves are reporting from this persistent homology computation is at every step of the filtration, how many homology 0 cycles we have represented with Betty 1, homology 1 cycles with Betty, Betty 0, homology 1 cycles with Betty 1, and homology 2 cycles with Betty 2. And uh, if these are new terms for you, I recommend going and checking out some intros on persistent homology in general. But just kind of colloquially, Betty 0 is computing the number of connected components in the simplicial complex at a given step. Betty 1 is, so here we have one connected component that consists of points 5 and 6 and the edge between them. And we have 4 other connected components where we have 0.1 in its own component, 0.2 in its own, 0.3 in its own, and 0.4 in its own component. And we see as we add edges, we decrease the number of connected components because here in this step 2 of the filtration, 0.1 and 0.2 are connected together, and the number of connected components then goes down by 1. However, sometimes when we're adding edges, for instance, this edge between points 2 and 3, at step 6 of the filtration, the number of connected components stays the same. However, at this point, we introduce this new topological feature, a hole. And these one cycles, these holes that are kind of highlighted in blue, that's what's being counted by Betty 1. Eventually, triangles and tetrahedra come and fill these in, and the hole that we see in this filtration eventually goes away, and we no longer have any Betty 1 in our simplicial complexes. Betty 2 counts the number of enclosed voids that we have, like the inside of a basketball, and the higher dimensional Betty numbers count higher dimensional voids. So we see that in the case of the distance matrices, we have this really kind of clear understanding of how the arrangement of the points in a point cloud leads to shape features that are then modeled by the sequence of simplicial complexes. And we can summarize these shape features with Betty curves or Betty numbers coming from a persistent homology computation. And the main reason that we're able to kind of use these tools is that these shape features are reflecting the underlying data because we're connecting nearby data points first. And in the case of a distance matrix, these are the low values. Now with correlations, we have less theory, and we do have some applications, though far fewer than with distance matrices. But we could do a similar thing. Given a correlation matrix, we could build a filtration of graphs that we then get from this filtration of simplicial complexes. Yet in this case, we want to follow the spirit of the analyses from before with the distance matrices, not the analysis on the nose. So here in correlation matrices, high values actually reflect high similarity between data points. So we actually want to add edges between the data points whose correlations are high values first. So in this case, we see that the high values of correlation shown in like the darker reds and oranges are going to be added at the earlier steps of the filtration, even though the correlation values are higher. And we could still, using this process of computing the persistent homology of the filtration of simplicial complexes, get out summaries of the topological features like Betty curves, and which are reporting the same thing. But it's a little less clear how the structure of these topological structures that we're seeing relate back to the correlation matrix. Before we get into why this is a reasonable thing to do, I just want to go back to that step of flipping the order that we're adding the edges in the filtration. When we have the correlations, we want to add the edges in order from high correlation to low. So when it comes to practicing, to the actual practice of data analysis, of correlation matrices using TDA, often the TDA software is going to expect a distance matrix as an input. So if you have a correlation matrix, you could still just input it into any of the traditional TDA softwares. All you need to do is just flip the matrix entry orderings. So one just trick to do this is multiplying the correlation matrix by a -1 and then using that as the input to a TDA software function that might be expecting a distance matrix. And you'll be able to get out persistence diagrams, Betty curves, any of the topological summaries that are output by the software just from doing that kind of little flip on the input correlation matrix. So why is this okay to do? One reason is that we can compute this persistent homology, these Betty curves, with respect to the filtration step. So in this, we're kind of throwing out information about the scale of the correlations, but we're still keeping the relative ordering of the entries. And in doing this, we kind of create topological summaries that are agnostic to that scale and instead focus on topological summaries that highlight the importance of the ordering of these edges being added to the filtration. When we do this, we can do this for known null models, and in that have these statistics that, again, are agnostic to the scaling used for the measurements that we might not be as confident in. But we could get these kind of statistical profiles for these null models, such as having random IID matrices and looking at what their Betty curves look like versus Betty curves for the distances between pairs of points sampled in Euclidean or hyperbolic space. Each of these is going to have as input a symmetric matrix, and it's going to give us different Betty curves based on these different types of randomness that we use to build these null models. And once we get these statistics, we could compare our data to these topological statistics gathered in this way. And then another thing that makes this a reasonable thing to do is that we could take our data and we can shuffle that in various ways to kind of destroy known structure in the data and see how these topological summary statistics change after we do that. And this can help extract the signal and the noise in these persistence diagrams or Betty curves. And we could also test to see the significance of the features we're seeing in the data relative to these shuffles of the data, as well as to the null models that we talked about before. So all three of these kind of steps in a data analysis pipeline, computing the persistent homology with respect to the filtration step and ignoring the scale of the correlation values themselves, computing distributions of these scale agnostic topological statistics for null models, and then going ahead and doing shuffle controls on the data to identify meaningful structure in the topological signatures of the data from that which is just noise, all allow TDA to be a really important and powerful tool for analyzing correlation matrices. Even when the kind of tying the topological features back to something as concrete as the shape of a point cloud isn't available in the sense of correlations, we could still do meaningful data analysis. So given that motivation, now I'd like to do just a kind of quick walkthrough of some software, which is really just a wrapper for a well-known and well-used Python persistent homology computation package. But what this wrapper is really good for is allowing the user to input either a correlation or a distance matrix directly as input to a persistent homology computation and extract out, in particular, Betty curves that are computed with respect to a filtration step rather than the scale of the correlation. So let's take a look at this GitHub repo and how you could go about running these functions on your own data. So if you go to this GitHub page, the first thing I recommend is looking at the README. If you click on that, you'll see some of the dependencies of this software, so things you'll need to download before you use this PyClick Top 2023 wrapper package. In particular, you'll need to get RIPSR running on your computer. This is the main workhorse that's computing the persistent homology inside. And the main functions that this PyClick Top 2023 wrapper has is compute Betty curves, which could take any type of symmetric matrix, a distance or a correlation, and it will output Betty curves that are computed with respect to a filtration step. And then once you compute these Betty curves, it also has a function to plot them. So here's what the website for RIPSR looks like. So you want to go ahead and download this. And then to make sure that these functions run on your computer, you could go ahead and run the following just example scripts here. And each one should generate figures that'll pop up And in the scripts, there's a lot of kind of just commentary sprinkled throughout. So hopefully reading that will be informative of how the different functions inside of this package work to come together to compute Betty curves and plot these Betty curves for any type of symmetric matrix, whether it's a correlation or a distance. Given the time, I'm just going to flash through some of these plots that you get running those three scripts and conclude by just summarizing again that TDA can be a really useful method of data analysis for correlation matrices, even though the theory is less developed than for distance matrices. Some reasons that we believe this is like a, still a fine technique to use, even though there's less of the interpretability of the topological features with respect to a point cloud with its like known geometry and shape, is that when we compute the filtrations with respect to edge density, this is using a topological construction called an order complex. And creating these topological summaries that are agnostic to that measurement scale of the correlations can be really important when we're not confident in the actual values of the correlations. We're just confident in the orderings. Also, being sure to compare our resulting topological summary statistics of our data to distributions of null models, as well as shuffle controls of our own data. These are also two very important steps in doing meaningful data analysis of correlations with TDA. And lastly, there's a software wrapper available called PyClick Top 2023. It's open access. You could download it from GitHub, and it is there for easy application of TDA to both correlations and distance matrices. So thank you very much for watching.